All right. So, wow, this is amazing. I'm so happy to see you guys. Um, just to get kind of a gauge of like kind of how much familiar we have with blockchain. Um, how many of you are familiar with Bitcoin? And say you'd be able to explain how Bitcoin works. Yeah. Okay. Okay. How many of you know what the UTXO model is? A lot fewer. Ooh. Okay. All right. So today, recognizing that a lot of us are beginners, I'm going to try to give a very pragmatic introduction to Ethereum. I'm going to introduce blockchain as well. Actually, smaller rest. Because we have the lights off. It's like really glaring. Yeah. Okay. Thanks, man. Okay. All right. So let's just get started. Okay. A brief overview about who we are as Blockchain at Berkeley. So, our mission is we say, okay, we seek to educate people. We want to expand blockchain integration through our consulting projects. And we want to foster innovation through research and infrastructural contributions. But if I had to put that into a nutshell, we're really here for the people, and we're here to build a community. And it's because of you guys and you guys that come out to our events that makes this possible. So, thanks. Overview of an organization. So there's a lot going on at Blockchain at Berkeley, and if you're looking to get more involved, there's like infinite things to do. You should definitely join our Slack for one. You can connect with the community. But if you're looking to more like formally join as a Blockchain at Berkeley member, these are some of our offerings. So starting with our R&D department, we conduct some original research in blockchain as well as run events and meetups just like this. So we actually host the Berkeley Bitcoin meetup as well, where we regularly bring in industry speakers to go talk about their area of expertise. We also have R&D project teams. So members from like Berkeley students will apply to the R&D department, and then they will be assigned to a team and work on cool things like writing a paper on futarchy or like implementing mental poker or something, like kind of the interesting ideas. Secondly, we have our education, which is kind of where everything in an org stems from. So we have the fundamentals course, the blockchain fundamentals course, which is actually open source and available online if you want to learn much more about blockchain. So it's a full accredited course offered through the DECENTRALIZED program, and it's like a survey of all the topics at a theoretical level. So for the developers in this room, we also offer Ethereum development workshops, which are being formalized into an actual course over the coming semester. So you can also take that if you're interested in actually coding on top of the blockchain. And then recently we've started an initiative we call education consulting, where we basically go to all of these like big companies who are just itching to know something about blockchain and teach their management teams, like, okay, the basics of blockchain, how is this going to be integrated? And we're building a new set of proprietary materials to work on that. Yeah, and we're also planning on offering a local version of that. So basically a one-day workshop you can come in, learn about blockchain and business and from a very pragmatic mindset if you're interested in that. Okay, and then we also have our consulting department where we have this last semester we had around 6 or so internal projects that were working on blockchain proof of concepts and directed at some kind of company. And one of those, one of our teams was actually an external project which was working with Airbus this last semester on another proof of concept for them. So this upcoming semester, we're looking to, we're going to have the capacity to support 3 external projects. So we're pretty excited. Airbus is continuing with us. We just landed Qualcomm as well, and then for the last project, we pretty much sealed ExxonMobil, and we're deciding between if we want to go with ExxonMobil or Inspur, which is this giant Chinese IT company. Yeah, so this is kind of an overview of who we are and what we do as Blockchain at Berkeley. This is by no means comprehensive. We have so many connections to the industry. We offer jobs all the time. We have partnerships where like students can basically work on projects and build this tab that we have with this company or ICO There's so many ways to get involved, and honestly, it just takes you to come out and give us the initiative, and we'll connect you with the resources to make it happen. Okay, so overview of the lecture. I'm going to first start by introducing blockchain and Ethereum. Then we're going to talk a little bit about, it's misordered, about the EVM. It's going to be a little bit more technical for those of you who are computer science minded. Today's event is meant to be a little bit more technical than usual because emphasis is on learning, not say on 10xing your investments. We're also going to talk about smart contracts and then dive into some interesting use cases that are enabled by Ethereum. Lastly, I'm going to try to sum up for you, these islands of use cases where blockchain tends to excel. I tend to think that use cases for blockchain is mostly a desert with a few oases. Trying to give you like a general sense of, okay, I hear these words in this use case, I think it might be a good one. All right. Okay, let's get started. Okay. All right, introduction to blockchain. So, trustless, consensus, distributed. Wow. All right, we hear these words all the time. Let's go ahead and define in detail what these actually mean. So, what is a blockchain? Okay, a blockchain is a immutable distributed ledger. All right, let's break that down. Immutable distributed ledger. By ledger, we just mean basically you can imagine like an Excel sheet or something, and you're just appending rows to this Excel sheet. And within that row, you can contain whatever information you want. You can store things like account balances, who owns certain assets, and if you want to get really fancy, you can store, say, memory and execution state of a computer program, all in this ledger. By distributed, it's just you have a network, a number of nodes or peers that are all just connected by this network, and there's no central point of failure. And the key thing is that you want it to design this network in such a way that even if some of these peers crash, or even if they're trying to attack the rest of the network and act maliciously, the network as a whole is still able to function. So this is typically called Byzantine fault tolerance. And why do we want this to be distributed? Because when there's no central point of failure, you can create this trustless system where you don't trust any individual in that system. You just trust the entire technology as a whole, and the technology, is very rigorous. You can like mathematically prove it and things like that. Additionally, it means it's uncensorable. So because it's not passing through some central entity, that there isn't someone who can just say, oh, you're not allowed to participate in this network. It's a very liberating, democratizing sort of infrastructure, if you will. So typically, whenever we think about uncensorable systems, like it was the libertarians who initially started this movement of trying to create a decentralized currency and trying to create Bitcoin. And they didn't like government, so you can imagine why they might like cryptocurrencies, because the government isn't able to step in and just print money. So immutable. Immutable, I think, is pretty simple. It just means that once you've put data onto the blockchain, like you can't alter it. And because you can't alter it, this makes this data auditable for business purposes. However, we have immutable data on this blockchain. We want to be able to update it somehow, or update some kind of state. So in order to update the blockchain, update the ledger, the network needs to come to consensus using some algorithm. And there's a few components that are also important as well. We need some kind of cryptographic identity. Basically, you can think of this as like a public key and a private key. A public key is kind of like an email address. If you want to receive email, you give someone your email address. And if you want to be able to access your emails and send emails like that, you need your password, which is like your private key. So when you have a cryptographic identity, this basically allows you to own things on a blockchain system, because presumably only you have that private key, so only you are able to make transactions and sign transactions is the key thing. The other thing is that if you do something wrong and you signed off a malicious transaction, they can attribute blame to you, because the signature shows that in fact it was you who signed this transaction. So That's kind of an accountability mechanism built into the system. What does it mean to come to consensus? It just means that in this distributed network, everyone agrees on the current state of the network. For example, in Bitcoin, that agreement is on, okay, how much money does everyone have to spend? Like, how do we make sure that no one isn't double spending the money, so to speak? And in Ethereum, that's much more complex, which we'll be going into later. And how do we come to consensus in this distributed manner? So you'll hear of several common consensus algorithms. You'll hear of the three main categories are proof of work algorithms, proof of stake, and PBFT, which is practical Byzantine fault tolerance. And the main innovation of blockchain is, in fact, okay, this blockchain data structure on top of a consensus algorithm allows you to build an open distributed network where everyone can come to agreement on things. There's trade-offs between these different types of consensus algorithms. So you might want to decide, okay, if I have if I choose a public blockchain, it might be a little slower than if I choose like a private one, but a public one is trustless. In the private one, I have to trust the other nodes in the network to some kind of extent. So there's different design choices that you can make when thinking about your particular blockchain use cases. Yeah, so also to kind of flesh out the mental model, like, okay, I'm talking very abstractly, this like ledger, this blockchain that just exists in the cloud somewhere. What is it actually? It's all of these blockchain systems are just software. So Bitcoin is software, Ethereum is software, and whenever you are owning an account or like owning an address, you're basically conducting it through this wallet software. So whenever you create a new wallet, it generates a new Ethereum address for you. So right here is a screenshot of the Coinbase page. The top one is the receive money. So basically, to receive money, you share your address, and then the sender will specify an address and an amount. So you can send me money if you want. That's my address. And then to send money, it's also very simple. You just specify an address, specify the amount, press send. It's so easy that grandma could do it. And this is this ease of experience is something that we want to move towards as an industry. This UX that Coinbase has kind of built out. Okay, there's also a few components of the blockchain so that the rest of the lecture makes a little bit more sense. At a very high level, you can think of transactions as the updates to the blockchain, the updates to the ledger. They just make some kind of change to the blockchain. And the key thing is that remember, we have this cryptographic identity, and these transactions contain the signature of the owner of this address. These transactions are contained within blocks. So there may be many transactions within a block, and usually there is. The reason why we want to have this block is you now have an ordered bunch of transactions, and this block makes these transactions immutable. Now, each of these blocks references a previous block, so that is how you form the blockchain. So you can think of the blockchain as the history of all transactions that have ever happened on the network. Okay, so now we're going to go into a brief overview of Ethereum too. All right, so this is the homepage of Ethereum. It markets itself as a blockchain app platform. That's what it calls itself. Like, what exactly is that? So you can think of Ethereum as a decentralized platform. It's designed to run these things called smart contracts. So the key thing is it is a blockchain, so it has these same, leverages the same advantages that blockchains do. So it has no single point of control or failure, and it's censorship resistant. It's a distributed state machine. So you can think, okay, whenever you have this block of transactions, that's like a state transition function from state A to state B. In other words, like you could just think of Ethereum as kind of like a decentralized computer where everyone is like sharing this computer to run their programs on it. Ethereum has a native asset called Ether. So this is what you guys are probably interested in investing in. but also it's kind of like the basis of value in this system. You need some kind of token in order to transact and otherwise align incentives. The Ether is also what's given out to miners for finding blocks and contributing to the security of the network. Unfortunately, today we don't have time to really dive into what mining works, but that's why we're here for 5 hours, right? So, okay, some comparisons between Ethereum and Bitcoin. So, Ethereum markets itself as a smart contract platform. It's designed to be very complex, very feature-rich. Like you want to run decentralized apps on Ethereum. The key thing and the key innovation about Ethereum is that it features a Turing-complete scripting language. So what this means is basically these smart contracts, you're basically writing programs to be executed on Ethereum, and you can write programs with the full expressive power of any modern programming language. So the theoretical side is that any app that you can build today in a centralized way, you can also now build in a decentralized way on Ethereum. And this is kind of a theme that we'll return to. Ethereum contrasts with Bitcoin in that Bitcoin is much more like a decentralized asset. It's designed to be very simple, very secure, very fault tolerant, very robust. Bitcoin's smart contract language is a lot simpler, and you can't get nearly the amount of complexity as you can in Ethereum. But that's not, the complexity is not part of Bitcoin's design goals. A lot of people say that Bitcoin is the gold standard. If Bitcoin fails, then the rest of blockchain is going to fail. Because if we mess it up with something so simple, how can we ever succeed with something as complex as Ethereum? So this kind of contrasts these two. Let me see. Okay, so some more comparisons. For those of you who do know what the UTXO model is, Ethereum uses an account-based model, so where instead of spending from previous transaction output, you have an account, which we'll also talk about more later. Other note is that Ethereum is currently on proof of work, and in the near future, it's probably going to move to proof of stake because proof of work is very ecologically damaging. It's not the most efficient. It's hard to align game theoretical incentives, things like that. But this is more implementation details and some more miscellaneous implementation details. The block creation time in Ethereum is every 12 seconds. So every 12 seconds, you're going to have, on average, a block. And this block is going to contain these transactions that are doing things on the Ethereum network. And the reason why we want to have a very short block time of 12 seconds versus the typical 10 minutes in Bitcoin is, say, whenever you execute something on Ethereum, you want it to pretty much happen very soon. You don't want to have to wait 10 minutes for any code to just be run. So although it manages to achieve this with a small block time, there's a lot of other incentivizing that Ethereum needs to figure out in order to make this possible. So you can read about the Ghost protocol later today if that interests you. Basically, there's a lot of competing blocks, and a lot of computation can be wasted. So you need to implement some kind of scheme to mitigate that. The exchange rate, the proof of work, okay. So Ethereum uses Ethash, not SHA-256 like Bitcoin does. And the main distinction of Ethash is that it's memory hard, and presumably you can't build an ASIC for it. So that's an argument that Ethereum is better suited for building an actually distributed, decentralized network versus ASICs, where you need to have very specialized hardware to participate in this consensus process. The exchange rate, so I left up the last time that these slides were presented back in March. So back then, the price of Ether was $17, and now it's $373 as of earlier this morning. So this kind of shows how much traction Ethereum has grown over the years. Yeah, I wish I could take questions, but for everyone's time, we'll have to defer to the end. Okay. Okay, I'll skip this slide. Yeah. So Ethereum accounts, there's roughly two categories of accounts. The first category is called like externally owned accounts. So all accounts have an address and an ether balance. But these externally accounts are owned by like people or corporations. It's like what you would own if you sign up to the Ethereum network. And then there's contract accounts, which is basically bits of code. You can think of these as like just autonomous accounts on this network that you can interact with, and no one quite has control over them. You can make transactions to it, you can call functions on it, but otherwise you can't directly control this contract account. So if you consider all the accounts together, that consists of the entire state of the Ethereum network. So as a system, Ethereum needs to agree on the current balance that every account has, the current storage state of every account, and like for example the contract code. This is all a part of the consensus process. And at every block, you're updating the state of the network. So this like refers back to that idea of okay, these blocks are the state transition function between the states themselves. And like yeah. So the reason why, actually, I'll skip this because this is comparison with UTX. So, all right. Okay, so now this is going to be a little bit more technical. We're talking about the Ethereum virtual machine. So like what the execution model actually looks like for Ethereum smart contracts. So it's the EVM that runs contract code. You don't write it in this very high-level Turing-complete programming language. You have a very like low-level, simple stack-based programming language that actually looks like JVM's bytecode. And as a participant in this Ethereum network, you're independently running this EVM code, and that's how you like verify that these blocks are valid, that the computation has been done correctly. So you can imagine that, okay, every node is like doing this computation. It might not be the most efficient. So more formally, what EVM is as the state transition function is you take some block state, which is like kind of the current state of the Ethereum network, the gas, which is required to run these computations. It's like the fees you pay for the computations. You have the execution memory. You have the transaction itself that you're running. The message, which is like metadata on the transaction. The code, which is the code itself, and as well as like more execution things like stack, the stack and the program counter. And then you feed this all into the EVM to yield the new block state and the new amount of gas that people have. So the design goals of the EVM is like, one, we want it to be very simple, because like this makes it easier to prove the security of your smart contracts. And also, it allows you to secure the platform as itself. Like, if we want to build something very complex and feature-rich, like if we keep the lowest level, the opcode level, the EVM simple, then we have a much better chance of like getting it right. We also want it to be space efficient, so that's just like another aspect. Deterministic. So no matter what, given those inputs of block state, gas, like program counter, memory, whatever, you want to always deterministically come to the same output. So this will actually restrict some of the things that you can do. Like for example, you can't do HTTP requests over Bitcoin. Over Ethereum. And it's also designed to. It's very specialized. So it has some built-in functionality for cryptographic functions like modular arithmetic and exponentiating and things like that. So you can think of, okay, whenever you have some contract in the Ethereum like Turing-complete programming language, which is actually called Solidity, you run it through the Solidity compiler, and that generates the EVM code. So kind of all of this complexity is like managed through this compiler. But at the base level, we still have this very simple stack-based language. So the first thing you might ask is, okay, what if someone just writes this function, while true, like it's an infinite loop? Because by the halting problem, we can't analyze code and tell if this is actually an infinite loop. So you have to introduce some mechanism to protect against, say, a denial of service attack. Because you could launch a smart contract that has this infinite loop, and then now the rest of the network is trying to execute this, and they're just stuck. So the solution is gas, which fuels this contract execution. So every little opcode requires some gas to execute, and depending on how expensive that opcode is, it'll require more or less gas. So for example, like a simple add opcode will require very little gas, whereas if you do like cryptographic exponentiation, that might be like extremely, like thousands of times more expensive. So each transaction will specify the start gas, which is basically the maximum amount of gas that you're willing to spend on this computation. And the gas price. So that's basically the fee per gas that you're willing to pay. So at the start of the transaction, you multiply the start gas times the gas price, and that's the amount of ether that's subtracted from your account. And if the contract successfully executes, then the remaining gas that was not taken from start gas is refunded back to you. But if the execution runs out of gas, or if it otherwise fails, then the execution reverts and you don't get refunded all of your gas. So you always want to specify start gas to be more than you think you will need. Yeah, just to like be safe and not waste money. Yeah. So what about this infinite loop? Technically, Ethereum will still allow this infinite loop because you could still write that code. But the thing is, now you have to fund this infinite loop, and you don't have, presumably no one in the planet has infinite resources to fund an infinite loop. So people are disincentivized to do this denial of service attack. You can still do this denial of service attack, which actually happens during ICOs, just from normal usage, but it's going to be very prohibitively expensive. So the takeaways from Ethereum is it's not about optimizing the efficiency of computation. Let me see. Because it's distributed, everything is kind of redundantly parallel. Like every node is verifying each block, so that means every node needs to run all of this code. But the thing is, this is how you can have and establish a very efficient way to achieve consensus on the state and a distributed network. The key thing is without needing a trusted third party, and which will gain you all the benefits of the blockchain of being censorship resistant, trustless, immutable. So yeah, generally running code on Ethereum is expensive because it's kind of like you have this global network and everyone is like putting their smart contracts onto this network, but everyone has to share the same resources because in the end it's always bottlenecked at the computational resources of one computer. So you're thus incentivized to, like, if you're able to do this computation off-chain and then secure it on-chain, that is a much better approach. And because it's, so you don't want to do things like machine learning on blockchain, for example. You probably want to do the machine learning off-chain and then like implement that, add that model onto the blockchain. Okay, so that was really technical. Now we're gonna get into some of the more pragmatic aspects. So smart contracts. Okay, so what is a smart contract? Like, let's finally define it. Let's examine what a contract is, right? Why do we ever want to write contracts? So a contract is just some kind of written or spoken agreement between these entities, and you want to write this out because if either of these parties violates this agreement, it allows you to then go to the court and have this contract enforced. Like it's kind of like a safety mechanism. Well, a smart contract is if you take the terms of this relationship between these entities and you actually write it into programmatic code, such that if you simply execute this code correctly, then it'll automatically enforce the terms of this contract. Now, the only thing left is you need some kind of trustless entity, trusted entity to run this code. Like, And if you have a trusted entity running this code, it means that literally this smart contract is inviolable. Well, on an intuitive sense, what is Ethereum good at? Ethereum is good at being trustless, right? So what about we have the Ethereum network run this code? And that is exactly what we do. So these smart contracts in Ethereum are executed by the network itself. There's no trusted third party, and literally no one can violate the contract. So if you were to violate a contract, that means you would have to subvert the entire Ethereum network and most likely also break the cryptography as well. So that's a very very strong safeguard of like the execution of your contract. So by putting these smart contracts onto a blockchain, you've essentially created a way to create to establish these secure peer-to-peer agreements that cannot be violated ever. It's mathematically secure, and it lives on the blockchain forever, and you can always interact with it. Well, forever as in as long as Ethereum exists. So it's a very powerful concept. To fill out this mental model a little bit more, you can think of these contracts as like autonomous agents that live inside this network. Generally, they're not doing too much. They're usually just chilling there, but they'll react to stimuli whenever you actually like poke it with a transaction. You make a transaction to it, which can call a function or send ether to it or whatever. And in order to carry out its code, it needs to have direct control over its internal balance, its internal contract state, as well as some notion of permanent storage. So this is why we have these components associated with the accounts in the smart contract accounts. So at a very high level, smart contracts typically fall under these 4 types of use cases, not exclusive. You might have any combination of these as well. So you can have smart contracts store and maintain data. So for example, you can implement a token, or you can implement an organization's membership onto the smart contract. So you can basically build a decentralized currency with a smart contract. Very simple. Other things like it can manage some kind of relationship between untrusting users. So because you have the terms of this contract like publicly available and you can read, any participant, like they don't even need to know the other participants in this smart contract. They just have to check the terms of the contract. I agree with this, and then they're able to now transact with other people in a completely trustless way. So this makes sense for things like escrow. Some smart contracts are simply acting like libraries. Like you don't want to re-implement the same thing at the same time. So for example, there's a smart contract that allows you to like it's like an alarm clock. You can set an alarm on this smart contract, which will then like poke your own smart contract at a later date, things like that. And then you can also implement more complex authentication schemes. So like, okay, only these accounts are able to do things on this smart contract. Okay, so the minimum example of a smart contract is like a token. So you see here we have like a constructor that basically takes in some initial supply, and we set it to the creator of this contract. And then all you need is implement some kind of transfer function. You just need to check, oh, does this person have enough money? If so, then subtract it from the sender, give it to the receiver, and that's it. This is how you can basically implement Bitcoin, like implement any cryptocurrency, like at a base level in 4 lines of code. So this is how Ethereum kind of brags about its power and its simplicity. Other things you can do is like, say you can build a decentralized DNS system or a registry. So I think last year or so there was like DDoS attacks on on some DNS server. Like imagine if instead of having this centralized DNS server, you had it distributed on a blockchain where every node has access to this DNS data. So like to implement this in a smart contract is very simple. You just need some kind of like register function, right? You just need to map some name like Max Fang to some IP address. Okay, and then another like slightly more complex example of a smart contract is you can do. It's very easy to do things like crowdfunding in a smart contract. So I actually built something called Ether on a Stick at a hackathon, and it allows you to put a bounty on the completion of arbitrary tasks. So, for example, you can have contributors pool money into this contract, and it's going to pay out to some pre-specified recipient if and only if the contributors to this pool vote that this recipient did some action by some due date. So the example use case that we talk about this is like, okay, there's some company that's polluting a local river, and the nearby residents are unhappy about it. Giving an economic argument, they're bearing the negative externality of this pollution. And whenever the local government is too slow or unresponsive, that's a problem. But because these residents are facing this negative externality, they're willing to pay to have this resolved. So what they can do is they can set up one of these smart contracts. They can set up an Ether on a Stick contract where they'll pool their money that will pay out to this company to clean up the river. And it's only going to pay out to this company if at this certain date the contributors to the pool vote that this company indeed paid out to the river. That indeed cleaned up the river. If the company failed to do so by that date, then the contract can you can automatically have people withdraw their money from this contract. So this is an example of how you can very directly solve these issues, like the free rider problem in Ethereum. You can set up an arbitrary incentive scheme. That's kind of the power of Ethereum. Yeah, and a lot of other use cases will kind of have this general theme of, okay, we can implement these economic primitives directly in a smart contract. All right, so let's talk about a few more novel use cases that are enabled by Ethereum. Typically, we talk about the very business-oriented use cases, but since this is an Ethereum lecture, we thought we'd talk more about the more interesting ones and slightly more technical ones. Okay, so decentralized prediction markets. The basic idea of a prediction market is you want to draw on the wisdom of a crowd to forecast the future. And it's been shown that prediction markets tend to do better than, say, pundits and experts, because usually there's someone in that crowd who has some information, information on this event, and allowing them to make money off of that information then makes the forecast much more effective. So you could set up a smart contract that's like, okay, who's going to win the 2020 U.S. presidential election? The key thing is that you need these events to be public and easily verifiable. We'll see why in a second. So we have this 2020 U.S. presidential election prediction market set up on some smart contract. Now, the participants in the smart contract will buy shares of Zuckerberg or Trump, and they'll pay a small fee to have this, to the market makers. And what happens is on the election day, you're going to have oracles on the network, which are kind of people who report on outside events. They're going to vote on who won, and these oracles are incentivized to vote correctly. If they vote with the majority, then they receive the fees that were paid to this market. Otherwise, they might lose reputation and lose their ability to vote on future events. So the ones who voted correctly then are able to cash out on the shareholders who voted correctly or who bet correctly are able to cash out on their event. To make this model a little bit more concrete for you, you can imagine that, okay, a probability is just like a percentage, right? And the share price of each market can accurately represent the market's prediction of the probability that an event will occur. So the probability that an event will occur. So if the market says that the probability of Zuckerberg versus Trump winning the
being president again.
yeah. Winning the presidential election is like 50 cents. You want it such that, okay, like if there's any deviation from that, I can make money off of it. So say the shares will resolve to $1 on election day if indeed Zuckerberg wins the election, if you're buying Zuckerberg shares. Say you have like some dirty information on Trump that you can release shortly before the election day, and you think that Zuckerberg's chance of winning the election is actually 70%. what you can do is you can buy these shares of Zuckerberg until the price of the Zuckerberg shares goes up to 70 cents. So what you've essentially done is you've acquired these shares that were worth 70 cents at the price of 50 cents. And in expected value, that is how you make your money, by like making the difference between like, oh, what the market says and where you think it actually is. And also the other thing is like, if you're like really sure, like if you have something like for sure that is going to make Trump lose the election, you have a mechanism to express that in magnitude. So you can buy a lot of shares, like borrow money from all your friends, like people are doing to invest in Ethereum, and then like buy the Zuckerberg shares, and you're like guaranteed to like make a fortune. And like hopefully the market will adapt to like basically what you were saying. Yeah. Okay, so some use cases of this. Oh man, we're a little bit short on time, but the innovation of implementing these decentralized prediction markets, on a blockchain versus like some central prediction markets is now you're able to do prediction markets on just about anything. So at its core, it's just buying and selling information, right? So you can do things like, oh, is this movie going to be a flop? And then bet for and against this event to incentivize people to, participate in this. And then there's Hollywood insiders who do know whether or not this movie is going to be a flop. So then they can bet like, yes, this movie is going to be a flop. And then you see the market move and you're like, oh, okay, now I have my answer. And the Hollywood insiders also made some money off of it. You can also do hedging and insurance. So whenever you buy fire insurance, you're basically betting that your house is burning down, right? So you could do this through a prediction market. You could say, will my house burn down, and vote yes. And thus you're going to receive compensation if your house burns down. Ideally, what you want is like some insurance company is like scanning around looking for these insurance contracts. They think, oh, wow, I don't think that person's house is that likely to burn down. I'm going to take the other side of the trade. So this is kind of, obviously there's some issues that you need to resolve with like moral hazard and aligning incentives and things like that. But this is more a theoretical exploration of what you can do. Because theoretically, you can implement an entire insurance liquidity pool on a smart contract where you don't have to deal with those expensive office and human labor space. You can have a completely distributed insurance company. Other things you can do is you can set up, say, like a security bug bounty. Like you can say, will my company be hacked? And with a hacker revealing their secrets. So now you're basically setting up this trustless contract where, oh, like some hacker, some security researcher can now be like, oh, like if I do this for sure, I'm going to get my money. So now if your company does get hacked, you have now been made aware of this vulnerability and they've been paid for it, and you don't even know who they are. You don't even need to know who they are. And then signaling. You can also do things like, okay, to sum it up, it's like putting your money where your mouth is. So on Kickstarter, a lot of investors are like afraid, oh, what if they're not going to deliver on time? What if they continue to delay? If you want to convince your investors and give them a sign of confidence, you can set up a smart contract that says, will my product deliver on time? And then bet very heavily that, yes, this is going to deliver on time. So what you're essentially doing is you're exposing yourself to financial risk on an event that you have control over. So you're showing to the investor like, hey, I'm willing to lose money if I don't deliver on time. So you can see that I'm very incentivized to, in fact, deliver on time. So yeah, the benefits to being decentralized is like one, as I mentioned, there's no restrictions on market creation. So instead of having like, betting on Trump versus Zuckerberg in like a bunch of different silos around the world, you can bet on any event, and you can have the liquidity of all of these events shared into a single market. That's the other main benefit. You can also enable. Okay, I'm going to skip through some of these. Okay, unfortunately. Okay. Yeah, I'm so sad. There's so much cool stuff. Okay, so I'm going to conclude with some generalizations of what you can do with blockchain apps. So blockchain in general is very good at solving coordination failures because you can encode any arbitrary incentive structures. So for example, you saw with the Ether 6 example how it easily directly solves the free rider problem. It's not to say that a lot of these can't be solved through some central entity. You can imagine that if the government in the Ethereum stick example was willing to, help coordinate the cleaning up of this river, that you wouldn't need the smart contract. But this is like a technological solution that you can always fall back on whenever some social coordination or fails to happen. So you always have this global distributed layer to fall back on whenever there is a coordination failure. It's also good whenever you want things like disintermediation or censorship resistant or like a very open network. The primary example of this is cryptocurrencies themselves. Like libertarians don't want some central bank, printing money. And also remember that we have these qualities of data immutability, integrity, auditability, and authenticity. But the thing is, you still need to secure the endpoints. And that's usually where the blockchain use cases break down. Because now, instead of trusting a central entity, you have to trust the endpoints. And no matter how secure it is within the system, if the data coming into the blockchain is not correct, that might subvert the security of your whole system. So this is something that you need to be careful about when thinking about your own Ethereum and blockchain use cases. So because blockchain is a distributed system and it's redundant, what else is redundant? We want our data warehouses to be redundant and our servers, right? So you can imagine that blockchain is also really good for very mission critical applications. You want it for very fault tolerant systems. I already mentioned the complete security. And then you can also have new organizational and governance models. You can implement a organization like a company entirely on a blockchain where the shares are just tokens, and then using those tokens you can do things like vote on proposals and things like that. So this all contrasts with centralized solutions. With the centralized solution you have deep internal integration. Because it's all under one entity, you can do a lot of coordination to say Facebook. You have a very cohesive user experience. Everything kind of fits into everything else in a nice way, as opposed to say open source software where everyone has their own preferences and sometimes things will break down. In centralized systems, it's a lot more efficient because instead of having 6,000 computers run your app, you have one server running your app. I think that's a lot more efficient. You can also have full control over your read and write permissions. So a lot of people say oh, I want to use blockchain for identity and access management. But fundamentally, what are you doing with the blockchain? You're taking some central database and you're now distributing it to a whole network of people. When you distribute it to a network, everyone has their local copy of the data. So how do you prevent them from reading their local copy? So there's some advances and things you can do with that, like homomorphic encryption and ZK snarks, but that's still a research area and something that you can also read about today if you write down JP Morgan Quorum if you want to see ZK snarks applied to Ethereum. And also, centralized systems are very fast and adaptive, and they manage complexity well. So why don't we have, say, decentralized Airbnb or decentralized Uber? I mean, you can implement, theoretically, all of this, the GPS, the tracking, the matching, the algorithms, in a decentralized system. But the key part where it breaks down is whenever you have disputes between, a driver and a rider. And you need to bring in some human level of judgment to then, go say, oh, I think it was the driver that was correct in this case. And since we haven't yet, solved the general AI problem, and we don't know how to encode this into a smart contract, if you implemented that, human, it would be a centralized system again. It would not be trustless again. So this is why a lot of the limitations of what we can apply blockchain to are at literally what can we, as a civilization, encode into a smart contract. The key thing that you want to keep in mind when thinking about use cases is always ask, why is a blockchain better than using some central database? Because in most instances that of potential use cases, you can come up with an alternative centralized scheme that would be more efficient, much more adaptable, much more scalable, etc. Okay, So I'm going to leave you with a kind of a vision of where I think why blockchain has the potential, a huge potential. So earlier I mentioned the Turing completeness of these Ethereum smart contracts. And with this Turing completeness, you have basically the ability to take any centralized app today. Theoretically, you can now write it in a decentralized way on a blockchain. And in that near infinite myriad of possibilities, I think there is definitely a few killer use cases in there. And literally, like the only limit to what we can use blockchain for is what we can secure and scale. So it's up to the technologists to really push forward the blockchain technology. And that's what I leave up to you guys. All right. So thank you guys.